All right. Hello and welcome to South Bay Systems. South Bay Systems brings you talks on systems programming regularly. We do not have affiliation with a company. We do not take money from companies for talks. We happen approximately monthly. We've been going pretty strong for a while. We occasionally bring you coffee chats whenever all of us are a bit too busy to bring you a talk. There are some of your wonderful organizers out in the audience here. If you see any of them and you would like to... Oh, ordering wrong. We've also brought you some past talks. Our past talks are up on the website of South Bay Systems. You can check up on it to see when we're doing talks in the future, and there are recordings and slides from previous talks. If you would like to give a talk in the future, you are welcome to join the sign-up form. We take talks in roughly everything in the broad spectrum of systems programming. You can read a bunch of topics. If you're doing cool technical work, it is very likely that you have something interesting to talk about, and we'd love to hear about it. We are also open to venues. LinkedIn has been very kind and generous in hosting us this time. If you have connections to other companies that might be willing to host some talks, and you can take like 50 plus unlimited upper cap, it would be very nice. And now thanks to our sponsor for hosting us.
Okay. Today we're sponsoring from LinkedIn Infrastructure Org. So super happy to have you all here. If you want to learn more about the work we're doing here, you can check out our blog, linkedin.com/blog/engineering. And you can check out some of our open roles if you want to see a little bit more about what it would be like to work here at linkedin.com/careers. We're mostly hiring for more senior roles right now, but definitely come on over to our website and check out what we have available. And that's the end of my spiel. I'll keep it short and sweet. And you're going to do the intro for Click? Okay.
All right. Today, for you, we have Cliff Click. I have listed all of his numerous great credentials there. He is here today to give us a wonderful talk on Sea of Nodes. He is the original implementer of this into JVM. If you don't know which JVM the hotspot JVM is, it's the one that you think of when you hear the words JVM. So I will now hand it over to him. Thank you so much.
So slides are broken because somebody didn't like how they map back and forth. I'm writing a tutorial. I got asked to talk about it. A tutorial on Sea of Nodes and compilers in general. The repo's there. It's open source, Apache v2. There are several variations of different languages people have been implementing as they found spare time to do so. But the one called Simple is written in Java. It's the one I'm working on. It's up to I'm in the middle of chapter 25. There's a lot of stuff there. And now we'll see there. So in the middle of the screen, you can see the URLs or not. Okay, fine. It's Sea of Nodes, which is maybe unusual for people here, and I don't know what the audience is. So I'm going to poll here in a second. So what is Sea of Nodes? Well, it's a compiler IR. What's a compiler IR? Anyone here know what a compiler IR is? Anyone raise a 2, 3, 4 handful? Okay, intermediate representation. More hands. Okay, most people. Oh, this is good. It's the thing that you actually hack to go make code come out of the compiler. Like you parse text, but you're not going to try and run the text or turn the text straight into machine code. It runs through an intermediate step, an intermediate representation, and you hack on that. So this is an intermediate representation. It's been used in Hotspot JIT for 25 years. It's very fast to build, to optimize, to do all kinds of things. Yeah, these slides are really, the spacing is all messed up, sir. I do not know what happened. Okay, we're going to roll with it. I do. We're not falling off the bottom or anything, so let's roll with it. If it gets bad, we might flip to the PDF. So think GCC-02 in 1/100th the time, and it's always fully debuggable. So that's a little unusual combination as well. So it's fairly high quality optimizing, and also I can completely fully debug it like it's unoptimized, both at the same time, which Java does all the time. And I can step through how that works, but I wasn't putting slides up because I'm out of time for slides. So the other thing going on is I'm intermingling control and data flow, which is quite unusual. So then I said SSA, which is another big jargon word, static single assignment here. Who here does not know about static single assignment? Da, da, da. Oh, not bad. About 10%. Okay, so by static single assignment, I mean every program name like X is equal to something. Every program name is assigned once statically. You can repeat assign in a loop. I'll talk more about it in a minute. It's basically the greatest buff and compiler technology in like 20, 30 years. It's a big one. And so when I say name here, for static single assignment, the name gets assigned something, I mean a graph node. Oh yeah, look at this. Your graphs are completely foobarred. All right, I'll talk this slide and we have to switch to PDF. Did Alex catch that? Eric, yeah, I will have to switch. Your graphs are completely not correct. Sorry, they're very artsy and art deco-y, but they're wrong. And so, and I'm off the bottom too. So the spacing's just wrong. Yeah, flip here. So go do it. So basically, when I talk about a graph here and nodes and edges in a graph, I'm really thinking about concretely the graph you'd write as a programmer. It's a data structure in memory. There's a pointer to it. One node is a data structure, has pointers to other nodes. That's nodes and edges. It's a graph. There's nothing special going on there, right? As an implementation for graphs, the ones I use have no edge structure. The node has a raw pointer to another node. That's an edge. That raw pointer is, right? Thank you. Anyhow, all the different ways you can talk about nodes and edges in a graph, they're all functionally equivalent. As a non-goal, I'm not going to do minimal SSA. If you've been in the business for a while and you've heard of minimal SSA, it's not important. Hotspot's not had it in 25 years and no one cares. We'll make SSA that's very close to minimal very quickly and cheaply. And in the rare case it's not minimal, no one seems to have noticed that the code wasn't optimized that way. Okay, so there are chapters. All right, I want to risk it all and pull up Finder. That was not what Alt-Tab was supposed to do. That says Chrome. Why did I blueprint plans? Where does sing? No, sir, we've lost the README. Yeah, hang on. Hey, there's a README. Oh, okay. It exists. Here's chapter 1. Here's chapter 2, 3, 4, 5, 6, 7, 8, 20, 20. Okay, who cares? A lot of chapters there. Preview. Okay. So chapters 1 and 2 are I'm going to turn into SSA an expression directly here. And there will be no tricks. This will be stupid and obvious. I'll be doing only the obvious things and get the obvious answer. But later when I do control flow, I will also do the same things, but it will not be obvious because it won't be on data, it'll be on control. If statements, returns, calls, that kind of stuff. So that's why you're going to get some pretty basic SSA stuff. But if you look at this, I have some text expression where I put something together. And in that first block there, that's a classic quad style IR from like GCC or LLVM from the 60s and 70s. There's an opcode, there's a destination register, there's some source registers. They're probably virtual at this point. There's an infinite number of virtuals, so it's all fine. I can alpha rename it to say, hey, I'll just use the pointer instead of the register name. Okay, once I do that, then I can take the square rectangles of the things and alpha rename them into circles with the opcode in the middle, and I have a graph. And these forms are all completely identical. It's just a reshaping of things. And that's why I talk about it as a graph. I find the graph just way the hell easier to think about. But you can lay them out any way you like, although when I get a little further along, I will lose the list format of the basic blocks, and the nodes will be free running in the graph, which is the C and the C of nodes. So I have nodes, they have USTF edges. Those are required for semantics. A minus B is not B minus A, so they're ordered. You have an opcode. You probably have def use edges to make life go fast. You have some other things in there, maybe a unique integer for better graph walking, maybe some constants, maybe some semantic analysis fields, things like that. But you really want to keep the nodes pretty light and free because the compilation speed is all about how small those nodes are. If your whole IR fits in your L1 cache, you can compile really quickly. Okay, so let's SSA here. The easy stuff, again, no secrets, no surprises. I'm going to do the dumb, obvious thing the dumb, obvious way, and then we'll get fancy in a little while. So there will be an expression stack because I'm parsing raw text. If you're parsing AST trees or you're parsing Java bytecodes, you have a little different parser layout structures, fine. There's operator precedence. I'm not going to talk about it because this is not about a parsing talk. I have a stack because I am doing expressions that I'm parsing. I have a symbol table, going to map X and Y to something. And if you're using Java bytecodes, for instance, the name would be the register number in the Java bytecodes. So when I say, hey, I'm talking about a name, or I'm talking about an expression variable, or whatever, kind of keep your head open as to what those things mean, because you can apply this in a lot of different domains. The symbol table has mappings to other nodes. X and Y predate dist equals x squared, or else you have an undefined variable. Assuming your program is correct, you have a mappings to X and Y. The stack starts empty. The parser only edges are in this lime green. And the trick there is that when I'm done parsing and building the IR, I'll throw them away. And so what's left is the IR I'm interested in. So those are all temporary, showing how I'm hooking things. So do it pretty easy here. I'm going to parse X. That just means table lookup in a hash table, classic stupid hash table. Get a node, push it on your stack. Oh, you got to multiply. Well, operator precedence parsing. Insert your favorite technique here. I don't care. That's not this talk. Moving on. Parse X again, goes on the stack. Oh, I'm done with the multiply. I'm going to make a node, pop two things from my stack, push the multiply node on the stack. I'm done with that first little bit. So like I said, no surprises here. This should be all very obvious. Same thing for the add, save it for later. Here's a Y, goes on the stack. Here's a second, oh, here's the multiply. Then the second Y. Then I do the same thing. I pop two elements from the stack, build the operator node, push it on the stack, pop two things, push the operator node, pop it on the stack. Okay, here I'm going to assign it. I'll put it in my map. The map for dist now points to the add, the result of the expression. And maybe it goes to a store operator. That's a little ST there. Kind of depends on what kind of language you're implementing, how you're designing things. And hey, look, that's just an expression DAG. And exactly it is. Since there's no control flow, SSA and expression DAGs are identical. There's nothing different between them. I'm showing uStef edges. You get DU edges by walking the graph in reverse. I populate them both typically because faster optimization down the road. Okay, that was chapters 1 and 2. In what, 5 minutes? Well, plus a lot of screwing around, so more than that. Peepholes. So I'm going to talk peepholes before I get to control flow, because in a minute I will do control flow with peepholes, and then it gets really weird. So first, peepholes. What's a peephole? Peephole optimization. That is a place where I look at the graph. I have these graph rewrite rules, and they peephole at the graph some small little region, and they discover a local fact about the graph in that region that you can optimize, you can do something with. And then you rewrite inside the peephole, and at the edges where edges cross in and out of the peephole, those edges remain, but they might point to something different on the inside of the peephole region, right? Okay, so now here's the magic trick. This shit is fast, provably linear. Probably half of all my performance gains come from peepholes. That's because I do peepholes on control flow, as well as data, as well as memory, globally across everything, because the sea of nodes lets me do it that way. So essentially, for no effort, I'm going to get a really massive, cheesy, easy optimizations, including the kind of obvious peepholes you think. I can also do forwards and backwards data flow in the same framework, in the same way. I do value numbering or common sub-expression elimination. If you see CSE, that's common sub-expression elimination. Fine. There are some things I don't do with peepholes, not in this talk. So loop unrolling, range check elimination on loops, massive inlining things, register allocation, cogen. The tutorial totally has inlining, and it totally has cogen and register allocation, but it doesn't do anything special with the sea of nodes. It uses sea of nodes during those phases, including register allocation, but there's nothing special about it. Okay, so peephole rules. There's going to be a work list. I'm going to look at the def use edges to find my neighbors. And when I make a modification to get thrown on the work list, and I'll repeat till the work list runs dry. The implementation of peepholes is typically I take a node as a C++ structure or a Java structure. I take a virtual call on it. That virtual call says, hey, I can reshape myself in some better way or not. Or I'll do constant propagation, I'm a new value, or I'm doing liveness, or I'm doing forward flow or backwards flow or whatever. A lot of things, including Hindley-Milner, I can do with peepholes this way. Dead code elimination and constant sub-expression elimination are technically a peephole, although they're the same for everybody. So it's shared one common implementation for those, which does the obvious stupid thing where you just, CSC, just look up in the hash table. And dead code, I just count my outputs and they're 0, then you're dead. And I'll do that in a second here. So let's go constant fold this graph. where I've discovered that y is 0 for whatever prior other reason I did. And so I'm going to pop my color-coded store off the work list, discover that it's not dead. There's no CSEs. I'm going to call this idealizing. Can it be made in better in some way? It can't. So there's no progress, and I'm done. And most of the nodes fall into that camp of nothing's going on, done. Pull a plus off, same story. It's not dead, no CSEs, no constant folding, no idealizing, done. Multiply, not dead, no CSE, but there is an idealizing rule that says multiply of 0 is a 0, as well as multiply of two constants is the constant. And I'll just do the multiply of 0 rule, but either one applies, they both work. And now I have a peephole, which I've circled in red there, little red dashed lines, which you can see the dash maybe. Okay, and inside I'm going to mutate. Outside I'm not going to mutate, but the edges that cross may point to something different. So I'm just going to replace by pointing to the 0 I got. And the inside has changed. I evacuated, threw something out, and the edges changed who they point to, but they didn't actually, the node in the graph outside didn't change. So that's a locally correct optimization. And that's one of the wonders and joys of hacking this shit, is that the people optimizations are all locally correct. And so the actual definition of a correct optimization is some really trivial, it's usually one line of code for the pattern match and one line of code for the rewrite. It's really easy. Put your neighbors on the list. Lather, rinse, repeat. Pull the plus off. Not dead, no CSE. Ideal says add of a 0. Yeah, I can do something about it. Okay, I'm going to replace it with the identity on my other input. Put the neighbors on the list, which will include the orange 0, which is already on. And go again. Pop the plus off. It's not dead. Oh, no, here it is. Sorry. So now put the neighbors on the list, which includes the store. Back up and watch here. What did I miss here? Yeah, the store's a neighbor. So the store goes on the list, which means the next step, I pull the store off the list. And he doesn't do anything, no surprise. And I pull the multiply off, and no surprise, there's nothing going on. And I pull the 0 off, and it's dead, so I'll throw it away. And then I finally clean up the store here, and I'm done. So back up was the obvious thing, right? So that's peepholes done on dataflow, does the obvious thing in the obvious way, and then we're going to move on to control flow, and we'll get more exciting. So in the sea of nodes, and this is the same compiler that Hotspot uses, like the C2 compiler Hotspot, this is exactly what's going on in Hotspot here. A little tidier and cleaner on the slides, but same down the line. There's a normal CFD embedded in the graph, but I'm going to put it in my funny graph format instead of in a two-tiered control flow graph of basic blocks. And along the way, I'll show some mappings between the two to help people get set in your head how it works, but there's never a basic block in C2 or in Hotspot. There's never none of that. It's strictly sea of nodes with these funny nodes, and they're all the same kind of nodes for both control and data. So it's going to look a little differently, but the same people rules will apply. Now, as I go, I will also, since I will lose the basic blocks, or I'll never have them in the first place, all those data nodes will just lose their basic block place. There will be no schedule, if you will. They will only have their location inferred by their uses and def edges. And later, at some point, I have to serialize the graph and make it a 1D line of program code. And then there's a straightforward graph walk that recovers a good layout. It won't be the layout you may have started with, but it'll be a good layout. It'll be the layout you would get out of your optimizing compiler. All the loop invariants get hoisted and things get dropped down in dominated tests and all that kind of stuff. And I don't need the edges for most optimizations, including all the CSEs and dead code and constant prop and inlining and a bunch of things. And the lack of them means that my pattern match rules, my people rules, do get to have this format that they're typically one short line of straight up Java or C++ code, just really no macros, no fancy shit, just a really if stupid thing, then one line to replace. And I can show some from the code online here in a minute. So starting point, here's my program text I'm going to parse. Has a tiny amount, so it fits on a slide, but x equals 3, else x equals 4. Really dumb, fine, going on. Okay, there's a start node. And start node's a little special. There's only one of them, and it's how you start your program. You can call it the main entry point. But if you're compiling pieces, parts, or functions, it's the place you'd start compiling from. And that means it's morally equivalent to the basic block 0 here. So I'm showing the moral equivalent basic blocks in these blue rectangles, but I'm not using them. Start's just another node, just like all the other little nodes. Data and temp in this example have come before, so I'm not showing you the code that produces data and x, or data and temp and x. reading a slide and talking when I read. But they have to have existed, and there's a map for them pointing to where they are using the green parser edges so I can find them. And then I begin parsing my text, and I come to an if, and for an if, I put an if node in. And morally on the basic block, I would put a jump of the test case, and then the block ends kind of typically in one of two targets. There's a list of targets you would go to in a basic block layout format. So there's something special about a basic block, then it refers to other basic blocks. Here, this if will refer to other nodes that will be morally kind of equivalent to basic block. Not exactly, but sort of. So basic block 1 and 2, true and false nodes. I butted them up close to the if so they look like they're attached. They're not. They're just other nodes. But they're telling me something about where the control is going to go. As a node, the true says I'm on block 2, or the false says I'm on block 3. Then I went ahead and parsed x equals 3. I updated my map. Well, I made two maps, one for block 1 and one for block 2. And I updated. Block 1 map points to 3. And then I got an else, and I parsed the other block, and x equals 4. Now I have two blocks. I had two mappings because I have two different pieces of code. And they might have updated all their mappings. I'm showing a trivial update. Many, many updates might have happened. And when it comes to a merge, I'll have two mappings I have to merge. And at that time, I'll have to think about what it means to merge mappings. And where the temp is the same on the both, so the mapping won't need to do anything, the x's are different, I'll have to do something special. So let's keep going down the line here. What? Oh, I went back. Never mind. Swide Max and I don't get along. It's all good. Okay, so I'm merging control flow. And for that one, I use a region, whereas an if will split your control flow, a region will merge your control flow. And regions can merge multiple. It can be 3, 4, 5 things merged. 2 is common, whatever. A merge of one control flow would be like a basic block that jumps to another one directly. And that has a people which is identity wipes out. So you don't ever see regions with one input, except until they come around the work list and get cleaned out. And then I have to do something with the 3 and the 4. This gets me to a phi node. Funny node, fake node. Pick your name of choice. People comfortable with phi nodes have enough SSA background. No one's raising their hand saying they want more. Fine. So the structure here is that the phi node has a pointer to the region to tell it which control flow path is coming in, and then it's merging either 3 or 4. Right, so pretty straightforwardly there. For people who don't know phis, I'll say it anyhow. They don't ever emit any code. Most modern compilers go SSA form at some point. They all have phi nodes. Phi nodes don't emit any code, but they force the register allocator to pick the same register for the two different paths, which often forces somebody to have a copy instruction inserted somewhere to make it work out. In this level, in this place in the compiler, and not just mine, in everyone's compiler where you have phi nodes, they don't have any code meaning. They just say pick left or right accordingly. So I just built some control flow right there. So I don't have the stuff on the left. I only have the stuff on the right. Actually, I've dropped the parser bits too. Okay, let's go to a loop. Here's a loop. This is the dumbest, shortest loop I could fit on a slide that was really a loop and it did something. Because it has to fit, and they have all these graphs of all kinds around. It's big, and so you have to make a small example or you run out of slide. So there's a start. There's a map for x and sum both to some 0. There's a basic block, which is your start, which has a register, virtual registers x and sum set to 0. Same for both. Whereas the prior example had an if that split and came together with a region to merge. Here I'm going to have the merge, one from the back edge, one from the fall in, go through the body, have an if, it's going to split, you're going to exit or you're going to loop. So I put a region node, but I don't know what the back edge is yet. So it's just a placeholder gets put. Same for the block, just a placeholder. Then I'm still at the loop head, and now I need something to do with what values come around the back edge. And because I don't know what's going to come around the back edge, I have to put a phi down now. This is where I don't be minimal SSA, because those values may change. They may not change. I have to deal with that as well. But if they change, I didn't have the phi, I wouldn't be able to find the right place to put the phi later. So I put it in now. And then there's an obvious stupid efficiency hack where I actually put in a lazy virtual phi and manifest it later. So you can make this as cheap as you like. But conceptually, I make a node and I put it in the graph. I then have the mapping on the right to hang on to the loop head, the mapping to the phis. And there's another mapping I hang on to for the body down here, basic block 1. So I have two mappings running around at the moment. Parse the test, x less than 10, and then an if. At the end of the block, I'm going to map it to the basic block side, or on the graph side, I'm going to say I have an if node, and I'm preparing to figure out how to split the situation. So I add my true and my false. The true exits. There's a mapping now for the exit path that tells you the value of all the variables when you exit the program. Maybe you don't care for x. We'll find out later, but you probably care about sum. Fine. The back edge for the loop body there, sorry, the exit case is being brought forward. The x of baby 2 is going to bring forward the values for x and sum. The test didn't have any side effects to modify them, or it would have been modified. Then I do the sum plus equals x plus plus, and you get this, a little more complicated, but if you stare at the red sum, it merges to 0. You follow around the back edge of an add of itself and x. If you look at the x guy, he starts at a 0, go around the back edge, follow that green arrow around, it's an add of 1 and x. So it's the obvious recursion happening here, cyclic graphs. I have inductions. In fact, if I want to look for closed form solutions of x plus plus, that's a trivial peephole, and in fact, C2 does that. So a lot of these programs that just do stupid little integer math and tight loops, he'll closed form solution them straight up by doing pattern matching on things like this. Okay, then I'm done parsing the loop, so I throw that mapping away, and I made the other mapping a little bigger. There's something going on here with x and sum when you exit the loop, which if I carry on parsing the exit path, I would just, whatever the map ends up, maybe it uses sum and not x, I don't care, whatever. But you get this. So some of the things to note here are that this is all very mechanical and dumb. There was no dominators tree, no dominance frontiers, no whole sweep over the program looking for some interesting fact. It's all completely local. And this will get you extremely close to minimal with only one more hack, which comes up in a few slides. So it's a graph. It's a control flow graph, but it's also this done with the sea of nodes style, which will make my life easier when I start doing optimizations on it. There's a start. It's the first basic block. There's a region going to merge generally 2 or more control flow edges. One gets peopled away. There has to be one control user. It's where the control goes after the merge point. There may be some fees, maybe 0 to many. Each fee will have as many data inputs as your merging control flow paths. There's an if, says I split. Control goes 2 different ways. The if could be a switch and have n-way splits as well. That totally also happens. Here, C2, the tutorial, it's all the same. Because of that, I can trace a control flow graph by walking the ifs and the regions and the trues and the false to start and just selectively on them. And I know whether a node is control or data by the opcode in it. There's a shortcut, obviously. There's some bit somewhere I can test fast. But this conceptually, the opcode tells you what you need to know. Same thing for walking through like calls and returns and everything you might think of with control. In the land of Java, there's also a throw and a try catch, and I optimize them to computed go-tos and directions, and that's all just control flow nodes. And the control flow nodes people like data ops as well, in that the people work list like can't tell, doesn't care, doesn't know. He just pulls something off the work list. Can you optimize yourself as a virtual call? Do you constant fold? Do DCE? Do you whatever? Value number. So let's do it. So people's on control flow. Let's assume in my little example here that temp is known to be 1 for whatever reason. Became true. Something happened earlier. I have a work list. I've pre-populated it. I have a graph. Fine. I'm going to pop something off the graph. So I pop phi because I'm working from the far right end. And I don't have anything going on. That's the common case. Nothing happened. Done. And I pull the region off. Common case. Nothing happened. Done. And I pull the 4 off. Nothing happens. Done. And I pull the 3 off. Nothing happens. Done. And I pull the false off. And oh, wait. False says I have this funny people rule that says my input is always an if. That's how they're generated. But the if's predicate input has a known constant value that excludes me. I can never execute. I am dead. This path cannot be reached by inspecting the 1. And of course, the 1 will actually be some type variable thing that will have a value in it that will be some range of things. But if it's true-ish instead of false-ish, the false will say, dead. So I'm going to rewrite defaults to a dead control. That X for X control, dead control. You cannot happen, right? And I unhook it false from the if, so that's taken out of there as well. And then I put the neighbors on the list, which is just region. I guess the if goes on the list, but it's already on, and I'm done. And I have this funny state of I have half of an if, but that's normal. That's okay. So I pop the region off. He has a people rule that says, I only have one live input. This is the only path that can reach me. I am an identity function on my one input. That's conceptually identity on control, but okay, whatever. It's like you had a basic block that fell into another basic block. There's no jump out or merge in. It's just a completely joined path, so you join them by having the region become an identity, which means he just folds himself away and says the bottom green arrow at the bottom points up to the true. He's gone. Now the fee needs to know which way he's going to switch, so I'm going to gut the region and say you're actually dead, but you know what path you're dying on. So I'm going to leave you in so the fees know how to do it. And when the fees all disappear themselves, the last use of that region will go away, and he'll be dead. He'll go away. Neighbors on the list. Pull a neighbor off. It's a fee. Fee says, my controlling input says there's only one path possible. I am not merging multiple values. I am just the one value that comes from the one path. So I need to clean myself up, become an identity on the one path. That removes a user from the region, the cache-treated region, so it'll be dead now shortly in a bit. Neighbors on the work list, go again. 4, it's dead, toss it. 3 is not dead, okay, leave it alone, carry on. That hacked region, it's dead, toss it. X control, dead, toss it. True, true says, wait, I have a peephole. My one input is truthy, I must be that input. I am identity control on the ifs control. So become it. Neighbors on the work list. The if is dead, toss it. The 1 is dead, toss it. Star's not dead, everything else is fine, so I'm done. So I did control, same way I did data there. In fact, I mixed control and data back and forth. And that means that all of the things I can do with peepholes all use the same common infrastructure for hacking control and data. I don't have a separate, I'm hacking a basic block out of a control flow graph, or I'm hacking some data ops in a basic block. It's all the same piece of code, which also makes for much easier to maintain and debug. Like you fixed it once and it works for the control, same as data. It's easy. Okay, so where are we at here? Okay, so I've run a long way really fast. I'm about to switch into memory is another big topic. Does anyone want to ask any questions about what we just looked at? Yeah. No stupid questions. Yeah. No, but if you look more than one node, you have the problem that your neighborhood gets bigger, and you have to have a tracking that runs further. And that happens in the tutorial, and I wasn't going to talk about it today, but the actual implementation says, by default, everybody gets to look one, and the common infrastructure handles it for the one case. So none of the pattern match rules, the one-line pattern match rules I'm talking about, they all take the default. It's just the one line. They don't have to do anything about it. It's going to happen for them. But for the guys who are 2 or more away, they'll put themselves on a dependency list. This pattern failed because this piece 2 steps away wasn't the shape I was looking for. That guy picked up dependency on this guy. If later this guy does change, he just grabs the dependencies and throws them on the work list. And that I can show the code for that. But it does mean that you can be non-local, but you have to add dependency in your people rule. I don't add edges to the graph. I add a dependency, which it's a pointer to a node, but it's not an edge in the graph. Okay, anyone else? Let's go do memory. SSA-based memory. It really has nothing to do with C of nodes. It's just memory as an SSA form. So I'm going to treat memory like a value, not like an effect. So memory is this big old honking giant thing, but it's a value like pi or some constant string. But because it's a mathematical value, I can make copies of it for free because mathematics says values are free to copy. Right? Of course, you can't do that in real life, but I'm going to treat it that way mentally, and then we're going to fix for how that works. Start will produce the initial state of memory, and a bunch of nodes operate on memory. So a call instruction obviously takes all the state of memory and mutates the heck out of it and returns you who knows what state of memory. So it makes a new state of memory. Phi nodes can merge memory states. Stores will do a targeted single chunk update on a piece of memory. Loads will read in memory and pull a value out of it, right? But it's being treated as a value, not as an effect. People rules work just the same. So phi on memory is identical to all the other phis. The code is unchanged. There's no if memory or not. There's no special memory phi. It's just the normal phi. It happens to have memory inputs. Stores and loads have some peepholes that are specific around them, just like add and multiply have specific peepholes, right? So back-to-back load stores or store or CSEs of loads, those are all very obvious peepholes that do the thing you expect to do. Okay, so the next thing, I have what I mentioned as memory is a big, giant, monolithic thing, gives me very low precision. So it gives me very poor aliasing information. It's correct. It will not optimize a lot of obvious memory things, so we want to do better. So I'm going to use equivalence class aliasing here. And I'm going to use equivalence class aliasing because it has a couple of key properties. The first is that I get it for free from any strongly typed language. Literally for free. It comes straight out of the parser. When I grabbed a guy, the parser looked him up in the symbol table, it had a type, that's my type. And I get to use that in the equivalence class aliasing. And I'll represent it directly in the graph without any separate aliasing structure. I'll kind of make this a key point. The graph is your aliasing information directly. The mechanics, the semantics of the graph is also the aliasing information. And the mutations to the graph mutate your aliasing information at the same time because it is the graph. And it's the same graph mutation code, central pieces that just do graph edits. They edit the aliasing, the graph that is aliasing at the same time with no changes. They're identical things. So it costs me nothing in the graph shape and graph design and the thinking about the problem where you get it from. It costs me nothing to have actually really sharp aliasing information available all the time. And it cannot get incorrect because it's just the graph itself. So what do I mean by aliasing equivalence class? I'm going to break up memory into these equivalence classes. Big old honking chunk, I'm sort of divide it, start chopping it into smaller and smaller pieces. And things in the same alias class always alias, and things in other alias classes never alias, and there's no may alias or might alias. It's either always or never, true or false. And if you're in the true case, you have an edge directly between you and you alias. And if you're in the false case, you do not have an edge between you and them, and you cannot find somebody who does not alias with you because you can't have the edge to go track them down. So class animal has some legs, some subclasses, cat and dog extends, meow and wags. Only cats have meow fields, and only dogs have wag fields, so they can't alias. But both cats and dogs have, we have the old slides. Fine, I updated this morning. And if you have legs, you obviously alias. And if you're in the abstract class, the bottom state actually only works if you're more precise on where you do animals. Like you don't ever use the animal type. So I deleted that piece there. And consider the thing on the far right is basically the right way to think about the problem. In the land of Java, strongly typed language, this gets me, based on IBM papers where they tried really, really hard 20 odd years ago to do better aliasing, this gets me more than 95% of what IBM's best Oracle level aliasing model would do on whole program analysis. And I get it for essentially free. So it's not 100%, but it's damn good. Okay, so now I'm going to do an example with memory effects. So, yeah. No. Wait. Feel free to ask and stop me because I talk fast. I go at a furious pace. If you don't understand something, surely somebody else does not understand the same thing. Feel free to ask. Aliasing is when I have more than one, I have a pointer to more than one thing. I have another pointer to more than one thing, and I'm trying to store into one and load from the other. And the question is, can they pass? Does this store crush the value I'm about to load? Right? So if I write to how fast my dog wags his tail field, and I load from how loud my cat's meowing, those are independent. They can float around relative to each other, and I don't need to stall one or the other. Okay, but if I'm talking about legs, I do. Okay. Yeah. The types came from the language. I can do type for inference on the graph as well, but I'm not talking about it here. So I have another repo called AA. I do a whole lot of really advanced typing stuff in it, including full program type inferencing using a combination of Hindley-Milner and the types I show here, which would be standard sort of constant propagation types, lattice theory stuff, which we can talk about today, wherever you want to go there. But here, these types I'm getting from the grammar from the language parser. So the Java C, Java parser has said, oh, you're an animal, you're a capital I integer, you're a capital D double, you're a capital N number. Those types tell me the aliasing I have or I don't have and turn into these equivalence classes. There's no type variables here because there aren't any in Java. Not in plain Java. You get generics, you get whatever you call it, type erasure. From the JVM level, there are no generics, there are no type variables. So go to AA, I totally have type variables, different story. And that's a whole nother talk. So I could do things with them, but out of scope. Okay. Okay, so in this particular program, somebody wrote a for with syntax sugar. Int I is from an array of ints. And this could be persons, an array of persons. Instead of saying sum plus equals I, it could have been person.compute tax, whatever, right? The iterator is, the key thing is the memory updates on the iterator, because what you actually got is syntax sugar for a new iterator object. The iterator has an X field that gets bumped, and it is using to gate the trip count by testing the loaded value against the length and by incrementing it. So there's a memory update right there. So the program I'm going to show you is the one that you get when you write the top guy, but what you really get is the bottom guy. And then he inlines has next, and you get this kind of a thing. And there's a memory update in the middle of the hot loop. So I have a program with a loop. And again, by the way, this is the smallest program I can do. It'll fit on a slide. I mean, I can't get any bigger. Sorry. Biggest program I can get fit on a slide. So I have a loop. It does the obvious things. It's missing all the parts. We'll talk about the parts. Across the top, I have control, kind of orange, memory in red, blue is data values. I have a pointer to an array of events. That's my one input. That's the ... down there, so wherever that came from. So looking at the data values here, there's a phi function in the middle. That's for your sum. Starts at 0. Falling down, you see the sum gets an add. Going back up, purple load from memory, from some address math, which we'll get to in a minute, from the iterator. The iterator is a function that drives the address math. And then the sum of the load and the original sum is looped back around, becomes the next value sum for the next loop iteration, and it exits the program live. Okay, here's memory. So here in the land of memory things, I have a phi of memory because I'm going to update the memory. And then I have 3 loads in a store. One of the loads on the left-hand side is doing a load from the iterator, add 1 to the iterator, store the iterator, store the x value, right? And then on the right, I have a load from the array length, which I'm going to gate the trip count, or range check elimination, or range check safety, which I'm not going to do. And then I load from the array body, which I'm adding on to sum. So I have 3 loads in a store in the naive version of this loop. Of course, altogether, it's a higgledy-piggledy pile, so let's not do that. Let's take a look at the memory state here. So I have an iterator plus 8. That's the iterator's X field. That X field will never alias with an array of ints. That's that strong typing. Like C, you can cast things and shoot yourself in the foot. You can't do that in Java. Strong typing, hard guarantee, iterator X does not alias with the body of an array or with the array length. So the array length at plus 8 and the array body, those are all guaranteed different. So the language semantics guarantees me that. So I have at least 3 alias classes here. Iterator X, array length, array body. So I'm going to make 3 versions of memory. That's my 3 equivalence classes. I'm going to break them up. In the next slide, I'm going to rebuild this loop as if I was using 3 different alias classes. And I get this. So the original one is untouched. That's the one that's the iterator X field. The middle one is the array length. And the array length did not get any updates. So the phi has a tight self-cycle. Of course, it's immutable, final. You can't do it. So I could have told you up front you couldn't update it. So I'll get rid of that phi in a minute. It's a junk phi. Any phi with a self-cycle it's a people rule. It says, I'm merging something and myself, which means I didn't merge anything. It's the same as the something. So I'll just delete it as a people and identity rule. And that, by the way, is the other missing piece of getting you to minimal SSA. Once you do the people self-cycle deletes, you're essentially minimal SSA. It's not exact, but you have to have really weird control flow to not get exact. If you have nice, well-structured control flow, like you use Java, you're guaranteed minimal. If you use gotos at the JVM bytecode level with an obfuscator to do horrible irreducible loops, you may not be minimal. But if you're writing Java code, this gets you minimal for free with no dominance frontiers and no fancy stuff. Okay, fine. The other one, of course, was the load of the array body. That's the third fee on the right. There are no writes in this loop. If there were writes, there would be updates. The fee wouldn't be a self-cycle. It's just a read-only, so it's a self-cycle. So it's a junk fee. So I'm going to get rid of the junk fees. I'm going to relay out the graph. I don't have any placement, so the graph is just a suggestion in memory. It's just a mathematical entity where the thing's live. There's no place there. So I'll relay it out, get rid of the junk fees. It looks a lot cleaner. And the relay out shows me something. The loaded array length in the far right, it's loop invariant. And my placement algorithm, which is coming later in the codegen phase, will totally move it out of the loop and be loop invariant. So the display is showing it loop invariant, but when I'm talking about it, there's no defined place where it goes. So there is no placement in the actual running of the IR at this level. Okay, what can we do with this guy? I still have, I have two loads in the loop body and a store. Can we do better? If I don't do better, you'll shoot me, right? This is like a dumbass thing. This has to be done better. Okay, so I'm going to push the load up through a fee. Another funny people rule. What's it mean to push it up to a fee? If I have an opcode down here and a fee here, if I want to push it up, I have to have a version of the opcode in every path. And that opcode output will be merged in its own fee. So from one fee, I'm going to get a second fee. And the one guy down here takes his inputs from whatever arm of the fee he get pushed through, which means he gets a more precise value. He doesn't get the merged value, he gets the pre-merged value. And with that more precision, I can get more optimizations. So I'm going to do the load here. Need a kind of a dynamic flow thing. It's a little hard to see. So I have two loads. The original fee is also there as original, but there's a new fee for the load on the right. And then the left-hand fee takes straight from the initial state of the world. And the right-hand fee takes from the back edge of the loop like I did before. So what did I gain here? Well, nothing unless I go to the next step. And yeah, the peoples have a profit rule on this one that says I have to make the next step or I didn't make profit, don't do it. And I'll do the two different pieces of profit here. One of them, I'll tell you it's easy. That load from the initial state, I made a new iterator, and I loaded from X out of the iterator. It's always a 0. So that load will disappear in a minute. But I pushed the other load down, because it's the next exciting piece. So I didn't edit the graph. I just relayed it out to be suggestive. Now I have a load store dependency, where since the load points at the store, they must alias. Since they point to the same address input, the purple input, it's a direct load store. And I can just do a load store elimination and say the load gets the value that the store is storing. So it's a peephole. I replace it without the store. And oh, look, I've pulled another load out. And furthermore, I've now got the induction variable, the index variable in a register. That's storing every pass through loop. It's storing into the iterator body, but the actual variable's now held only in registers. So I'll do a little relay out here. It makes it more obvious. And then I'll look at this here. This here, now I have another peephole. The store points to a fee, points back to the same store. No one else is updating memory except this one store. He's hammering the same location in memory over and over again. Bang, 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 bang. That's a peephole that says, don't do it every step, just do it at the end. So the change is the store, the fee will take from the fee itself and not from the store. And now I've moved the store out of the body of the loop. And I have a junk fee, which I can get rid of. And I get this. So now I have a loop that has one load at the top right for the array length, and a +1 spinny and a load in the body, pull up elements that you're adding into sum. You can't get rid of that load. And then at the end, there's a store down of the last index variable into the iterator object. So I've in-registered the iterator's X field with dumb local people rules only. And I get this as a whole thing. It's a big pile, but it's not too big. It's everything we had before lumped up here. So there's control around. There's an upper left corner is the array length coming in. There's the 0 for the initial iterator value. There's a loop for the iterator here. Then you load the array math out and get the load for the sum, and the sum's in blue spinning around. And the iterator's final output gets stored here. And you might notice at a future optimization that the address for the iterator is not being used by anybody but the final store. So I have a store into an object with no one else using the object. The store is dead. And because no one else is using the object, now the object's dead. And I can get rid of the object too. And these are all peephole rules. So there's a little weak form of escape analysis going on there. Okay. I have a fun IR. I love it. It's like any IR. It'll scale to the size of your compilation unit. But you can keep the individual nodes really small because they don't need to carry a lot of stuff. Yeah. Yes. Yeah, yes. So you are correct. This is incorrect. I yanked it on my slides this morning. These are old copy of slides, so it doesn't belong here. Sorry. We had some PDF graph shuffle issues, USB-C versus HDMI. All good. Yeah, whatever. Okay. I have an IR. It has control and data in the same graph. I can walk them both. I walk them with generally very fast bit set to being visited because it's a graph. It has cycles. You have to know you visited or not. Because the nodes are small and they actually map sort of one-to-one to other people's kinds of nodes, my compilation speed scales with the size of the IR nodes. And I typically, for C2, fit small to medium methods in the L1 cache, and bigger methods will be in L2. And that's part of the speed of the operations. The other one is these peepholes are really quick to execute because they're so stupidly short. There's so little code involved in them. And I'll show you some examples here. We get time because we're going to run out. And I can talk on forever. So I hear the question. Let me finish, and then we'll take a question, and there'll be open Q&A, and we'll do what we do. Peepholes, fun stuff. They cover a lot more ground than people give them credit for. Or they can if you design your IR to mesh well with peepholes. And they're easy to write and debug, at least in my opinion, because they're entirely locally correct. I can just look at this local region, and I better be able to tell that it's correct or not locally, right? And even memory is a local peephole. And aliasing I get for free by construction here. It was the graph. The memory's edges are effectively your aliasing information because that's what equivalence class aliasing gives me. I have a bunch more chapters. I ran out of slides and I ran out of talk time, and I'll run out of voice too. So global code motion, that's that unwinding algorithm I talked about. It's 2 linear passes, one forwards, one backwards. Push things as far up as you can go, push them as far down as they go. And then in the range of motion they have in the middle, you pick the best spot, which would be out of the loops and most control dependent, whatever. I did a bunch of language extensions in the tutorial, things like operator plus equals, var and val, type inferencing, so var val auto variables, trinary question marks, the calls and call inlining and stuff. There's like 24 language extensions. The language in the tutorial is on purpose nobody's language. And it's not intended to be anyone's language. It's just the scaffolding that you're going to build a tutorial around. It's actually reasonably usable, but that was not the goal. I get to code gen a couple more chapters, instruction selection, which will be nodes, but there'll be machine-specific nodes that do things like an x86 add for memory with an addressing mode or whatever. Register allocation. I finally do encodings, and I write out to ELF files. So the chapters that are in there now go all the way out to producing a standalone ELF file that you can just run. And I'm out of slides, and I'm out of time, so it's Q&A time, except you're first. Yeah, right. Okay. So in the land of C2, a common bad bug was that you didn't get termination because you do a peep and then you did peep and you did. Okay, fine. So those got beaten out by hard work, and then I figured out sort of the right pattern, and I now do something that's what I'll say it's essentially a variation of Church-Rosser's one-step property. There is the infinite state space of graphs you could have, and if you mutate something, you get a new graph that's been mutated from the last one. And if you mutate the left way, you get a new graph. But then these two graphs each are one step away from the common of either one of them. If you apply the other end of the rectangle of this, I have two transformations I can apply. I apply one go here, I apply one go here, I get these two graphs. I apply the other one here, I apply the other one here, I get the same graph. So the tutorial guy hard forces that with asserts. There's nothing to do at runtime. There's just some asserts that catch you if you screw it up in your peepholes. Usually you add a new peephole, that implies you must add another new peephole. Does that make sense? Okay, so I give you the guarantee that you will always get the same identical graph in the end, irregardless of workspace ordering. They're independent of the workspace ordering. And then that goes hand in hand with linear time and all that kind of stuff. You get all the big wins out of that. Because I don't have anything deep, because the edges are direct. So this is a big one. Because it's so subtle, no, people don't catch it until they've actually paid the price. I work with tons of compilers over the years, and I see this all the time. So the nodes and edges, they are direct pointers. There are no edge structures. So we'll make an effort to try the MacMe to the code. And we lost the code. We didn't lose the code. Maybe we got something here. Okay. Let me go to chapter 4. So each chapter is built on the prior chapters. It has everything the prior one does, plus more things. I want the source code. Actually, if I don't want this one. What are we doing here? Where is GitHub's source code? Oh, here. I have a mouse. Holy crap. Oh, I got a mouse. Life is good. Oh, source, main, Java, simple, blah, 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 node. Okay, add, Boolean, constant, div, minus, mul, node. Here we go. So there's like a dozen nodes. There'll be 24 by the end. Yes, you can load. You have internet. There it goes, internet. Oh, internet. Oh, God. Okay. So a node has a unique ID. It has a list of input nodes, has a list of output nodes. Now, it's Java done the Java enterprise style, so it's array list. In a better version, these would be bare. I would lift the array list up one level and put the body of the nodes, or the array of the nodes here, along with some indicator of the length. And C2 certainly does that, and they're just jammed back to back to back, so you get even tighter node layouts. But it's just, there's no edge structure. A node points to a node. And that's, you pointer chase, but if you're all fitting in L1, it doesn't matter. It was never worth it. So I did try in the beginning to have 16-bit indices into the arrays of nodes so that the node pointers were 2 bytes instead of 4 bytes. And that limited me to 65K unique nodes, which cut off the compiler on very large functions. And then the loss of performance on very large functions was like a hard kill. So people said, no, just double the node pointer size. Fewer things fit in your L1. I was already 100 times faster than my competition, so no one cared. Right? I got 5% slower, but I'm still 95 times faster. No one fucking cares. So the answer was, you still want the small for speed, but if you eat a big one, you do. And that's only occasionally happens. So the other thing going on here is that the incremental benefit of inlining into a big function just keeps decreasing, right? As the function gets enormous, the next inlining piece doesn't really help unless it's in the hot inner loop. So you focused inline, I have profiling data, I can do profile guided inlining, totally do, okay? So the programs don't explode with the compiler guessing I need to inline one more level and then get these giant IR wads. They don't. You get whatever the max IR wad you get out of a Java JVM method, which is limited to 65K bytecodes. After all the safety checks and everything, blah, 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 pops in, you get 100K, maybe. You inline your way up to 150K nodes. It's fitting in your L2. Good enough. Well, why don't we take the break, and I'll be here for questions.